The next application of derivatives we're going to look for is an extension of some of the work that you have done with quadratic equations in Pre-Calculus 10, where we're trying to find a maximum or a minimum quantity of some sort of variable. So here are the general steps for solving an optimization or maximum and minimum problem. Okay, so I'm just going to put in brackets here that this is a maximum or a minimum. So if you see the words maximum or minimum, this is an optimization problem. So first we're going to express the quantity to be optimized in terms of only one unknown. So only one unknown quantity, basically only one. The quantity you're going to optimize, you want the other side of your equation only to have one variable. Okay. Number two, we're going to find the absolute maximum or minimum of f of x on its domain. So often with these optimization problems, there are going to be some limitations, okay? And we're going to have to compare by comparing f of x at critical points and endpoints. Okay. So example number one. And these are, as we noticed with the last section, these are everybody's favorites, word problems. A rectangular swimming pool, let's call it a swimming area, on a beach needs to be fenced off with 2,400 meters of rope. What are the dimensions of a swimming area with the largest possible area? Okay, so we didn't see the word maximum and minimum, but we did see largest possible. So you see a largest possible, the smallest possible, minimize, maximize. Those are all going to be clues that this is a problem that you will solve using optimization of some sort. So we have a beach. It's a sunny day, so we had better bring a beach umbrella. Okay, and then we have some water at the beach. Okay, so now what we're going to do is we are going to draw, we have a rectangular swimming area. Okay, and let's assign a variable to the sides. So these two sides are of length x. It's a rectangle, so they're the same size. So we have 2,400 meters of rope. So that means for this entire three-sided thing, we have a total of 2,400 meters of rope. We are going to be taking away the amount that we're using on the sides. So we're going to be using 2x meters of rope on the sides. We have 2,400 in total. So the remaining side is 2,400 minus 2x. So now we want to write, express the quantity that we want to optimize in terms of only one unknown quantity. So the quantity that we want to optimize is the area. We want the largest possible area. So area is equal to length times width. Okay, so this is equal to x is our length times 2400 minus 2x. That is our width. Okay, so we're looking for now the critical points. We need to find critical points and endpoints. Okay, well, the endpoints are going to be x equals 0 or x equals half of 2400. So x equals 0 because you can't have anything that is less of a rectangle than a straight line. When x equals 0, our area is 0. When x equals 1200, our area is also 0. So the endpoints are not viable options in this case. We're not going to have a rectangle that is really just a straight line. That doesn't have any area at all, so it's not useful for us. So we are now looking for the critical points, which means we're looking for places where dA with respect to dx equals 0. We're going to take the derivative of the thing we want to maximize with the variable with respect to the one variable that we've gotten it down to. So A is 2400x minus 2x squared. A prime is 2400 minus 4x. Let's plug in 0 as 2400 minus 4x. And so x is going to be 2400 divided by 4. So x is 600 meters. Okay, and that will give us our optimal. So let's just check to make sure this actually is a local maximum. Okay, so A double prime is going to be -4 because we have 2400 minus 4x, so the derivative is -4. So A double prime is less than 0. That means A is concave down. And so we have a max at x equals 600 meters. Okay, but we haven't answered our questions, our question fully yet, because we're asked for the dimensions. So we also need to figure out what 2400 minus 4x is. So 2400 minus, we have to figure out what 2400x minus 2x squared is. So we have, not 2400 minus 2x squared. We need to figure out what 2400 minus 2x is. So 2400 minus 1200 leaves us with 1200. Okay, so we have our dimensions are 1200 meters by 600 meters. That will give us the largest area. Okay, and we did check the endpoints at the beginning, but you may formally want to check the endpoints. So I'm going to put a star in just to make sure that you check the endpoints, which is A of 0 is 0 and A of 1200 is 0. And I have been known to put sneaky questions on tests where actually one of the endpoints is going to be your answer. So don't forget to do that. Okay. So example 2. Completely different kind of question. So we're going to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Okay, so let's draw a picture of this situation. Okay, we have a parabola y squared equals 2x. So we know that when x is 0, y is 0. When y is, we have this point here, we want 1, 4. When x is 1, we have 2. Y squared is 2, so that means y is going to be root 2. Which is a little bit below 2. It's going to be right about here, about 1.5. Okay. We have a point 1 comma 4, and we want the shortest distance. So that means that's going to be the line that's normal to this parabola here. Okay. So what exactly are the coordinates? We know that this point here is 1 comma root 2. What are the coordinates of this point here? Well, we're going to write them in terms of a single variable. And so we don't have to take any square roots. It's actually easier to write x in terms of y than y in terms of x. So we have a relationship between x and y for this point. So this point up here is 1 comma 4. So we know that y squared is equal to 2x. So x equals y squared over 2. So the coordinates of the point we're looking for with the minimum distance is y squared over 2, comma y. Okay, so that's our x coordinate of that point. So we are looking to minimize the distance, so let's write an equation that relates the distance to our values of y so that we can minimize it based on y. We're looking for y values that give the minimum distance. So this is our distance d. So d is equal to the square root of x2 minus x1 squared plus y2 squared, y2 minus y1 squared using our distance formula. Okay, so now we're going to use x equals y squared over 2 and y, so our distance still, is equal to y squared over 2 minus our x coordinate of the point we're trying to get the distance to is 1 plus y minus 4 squared. And this looks like a super, super fun equation. Okay, so we're going to be taking the derivative of this. So now we're going to go for d prime. Okay, so what do we have? Chain rule. We have a radical. Inside the radical, we have stuff squared. Okay, and inside that first radical there, we have also stuff squared over 2. So we need to make sure that we are multiplying by all of that. Okay, so the first thing we deal with is the squared. So this is to the 1/2 power. So the derivative of that is going to be negative. It's going to be 1/2. So we're going to have a denominator. And we're going to have a 2 in it times the negative, that whole what's inside to the negative 1/2. So we're going to have a square root of everything that's in there in the denominator. And that takes care of my square root. So we have radical y squared over 2. We don't change anything. Minus 1 squared plus y minus 4 squared. Okay, now that's going to look scary because we have that in the denominator, but we're actually not going to need to worry about it that much because we're looking for where this is equal to 0. We're looking for critical points. And as we're looking for critical points, we don't care about where this is going to be equal to, where this is not going to exist, because anywhere d prime doesn't exist, we're not necessarily going to be using for this case. Okay, we really do actually want it equal to 0 here. So now we have to take the derivative of stuff squared. Okay, so we have derivative of stuff squared. So for our first derivative, we have 2 times y squared over 2 minus 1 to the power of 1, but we also have to multiply by the inner derivative. So let's deal with that. We have one of the squareds, but we have to deal with the inner derivative, which gives us 2y over 2, which is just y. Okay, so times y plus 2 times y minus 4. The inner derivative here, though, is just 1, so we don't have to worry about that. We could just multiply by 1. Okay, so that was kind of a yucky derivative, but it wasn't too bad. Just 3 instances of the chain rule we had to deal with. Okay, so let's look at where this is equal to 0. So this is 0 when the numerator is 0. So this is 0 when 2y times y squared over 2 minus 1 plus 2y minus 8 is equal to 0. So this is 2 when we have y times y squared, 2 times 2, so we have y cubed minus 2y plus 2y minus 8 equals 0. That gives us these cancel beautifully, so we get 8 equals y cubed. So we get y equals 2, and x is going to be equal to y squared over 2, but 2 squared divided by 2 is just 2 also. So here the point is 2, 2, and that is going to give us our derivative here. Okay, example 3. You own a soda canning plant. You want a can that maximizes the volume for the least amount of material and holds 500 milliliters, which is the same as 500 cubic centimeters. Okay, so you want biggest volume, smallest amount of material, and we're given a constant for our volume. So what we're really going to be trying to do is not maximize the volume, but we're going to be trying to minimize the surface area. So let's write down a couple of relevant equations. We know that for a can is called a cylinder. So we have a can, looks like this, and we're going to assume it is a perfect cylinder, which we know soda cans are not. And they have a radius and a height. So the volume of a cylindrical can would be pi r squared h, and the surface area is 2 pi r squared plus 2 pi r h. So this right here is the quantity we want to minimize, is the surface area. But we know it's going to relate to volume in some way. How is it going to relate to volume? Well, here is the problem. When we look at the surface area formula, we see we have not one, but two variables, and I'm going to want to get rid of one of these variables. And because this variable only occurs once, and it's not squared, there's nothing that's done with it besides multiplication, I'm probably going to want to write h in terms of r. So the only thing I know, the only bit of known material is what the volume is. So I'm going to plug in the number I know for volume. I have 500 equals pi r squared h. And I'm going to use the second equation to write down what h is in terms of r. So h is equal to 500 divided by pi r squared. Lovely. So now what I can do is I can substitute this into the surface area equation, which will give me finally an equation with just one variable. So I have 2 pi r squared plus 2 pi r, and I'm going to write, instead of h, I'm going to write 500 over pi r squared. And now I can do some canceling. So I get surface area is 2 pi r squared plus, this cancels that with that, one of our radiuses cancels, 1000 over r, which is the same as 1000 r to the minus 1. So now I'm going to take the derivative of surface area. So surface area prime is 4 pi r plus negative 1 times 1000 to the r to the minus 2. And now we're going to plug in 0 and try to solve this. We have 0 equals 4 pi r minus 1000 over r squared. You could also have used the quotient rule on 1000 over r if you wanted to. So let's multiply by r cubed So we get 0 is 4, sorry, r multiplied by r squared, 4 pi r cubed minus 1,000. Rearranging the equation and dividing by 4, we get 250 is pi r cubed. And rearranging again, dividing by pi and taking the cube root, we get r equals the cube root of 250 over pi. And that radius is about 4.3 centimeters. And 500 over pi times 4.3 cubed will give us the height, which is approximately 8.6 centimeters. So it's about double the radius. So now we want to test if it's the minimum. Okay, so we have to test that it's the minimum. We could also try doing doing the endpoints, but we're just going to make sure it is a minimum. So we have our surface area double prime is 4 pi plus 2,000, multiplying by -2, r cubed, r to the -3. So when r is 4.3, it is positive. Okay, r equals 4.3 gives us a SA double prime is greater than 0. So this means we are concave up at r equals 4.3, which means we have a minimum. All right, last question. We like the river. These are these river kinds of crossing questions and who's going to get there first and all that fun kind of stuff. So a man is at point A on the bank of a river 3 kilometers wide. He wants to reach point B, which is 8 kilometers downstream on the opposite bank as quickly as possible. He can, we'll assume he has a boat to row. He can row at 6 kilometers per hour and run at 8 kilometers per hour. Where should he land to reach point B as quickly as possible? Whew. The first thing about this question is where to start. We have a man at point A on the bank of a river 3 kilometers wide. He wants to reach point B 8 kilometers away. We're not going to take current into account, but some problems might. On the opposite bank as quickly as possible. He can row at 6 km an hour and run at 8 km an hour. Where do we want to land the boat as he crosses the river to reach point B as quickly as possible? So let's start by drawing a river. How wide is our river? It is 3 kilometers wide. Okay, so our man is starting here at point A. We want to reach point B, which is 8 kilometers down the river. Okay, so we know that the distance from A across the river is 3 kilometers, and we know that B the total distance along this way is 8 kilometers. Okay? So we want to know where he should land. So what is this point right here? And we'll call this distance x. So x kilometers down the river. And we'll call this, so if this is x and the total distance is 8 kilometers, this is 8 minus x. And he's going to travel a distance d across the river in order to get there, and then he's going to run 8 minus x kilometers. And we want to minimize, so what do we want to minimize? As quickly as possible. We want to minimize time. Okay? We know his speed. So what we are going to need to do, we also know that our speed equals distance divided by time. So that means time equals distance divided by speed. Okay? So we have 3 kilometers, x, and d. We are going to have to find our distance d. We can use the Pythagorean theorem. It's going to be the square root of 9 plus x squared, because we are x squared plus y squared equals d squared. Okay, so we have 2 different times that we're going to be looking at. So we're looking at our total time, and we want to write it all down in terms of x. And now we only have x variables now that we've gotten our d in terms of something else. Total time equals the time we run plus the time we row. So we're just going to add, time just adds. Okay? So our time we run is equal to the distance we run divided by the speed we run. So that's going to be equal to 8 minus x divided by 8. So he rows, if you guys can remember, we run at 8 kilometers per hour. He rows at 6 kilometers per hour. So t row is equal to the distance we row, which is radical 9 plus x squared, divided by the speed he rows, which is 6. Okay. So our total time, we'll call it t, equals 8 minus x over 8 plus radical 9 plus x squared over 6. We're going to differentiate t now, because that's what we always want to do, is we want to differentiate the variable we want to minimize or maximize. This is going to be derivative here, negative 1 over 8 plus 1/6. We're just going to factor out the 6 and then deal with the radical. This is to the power of 1/2. So it's times 1/2 times 9 plus x squared to the negative 1/2 times the inner derivative, which is 2x for our chain rule. Okay, simplifying, we want this to be equal to 0. We get negative 1/8. We can take this 2 and cancel it, which makes things a little bit easier. We are left with an x in the numerator because that's a negative exponent. So, sorry, did I write negative 1/2 instead of negative 1/8? That wasn't right. Plus x over 6 in the denominator, radical 9 plus x squared. So simplifying, we get 1 over 8 equals x over 6, radical 9 plus x squared. Multiplying by 8 and multiplying by 6 times 9 plus x squared by both denominators, we get 6 radical 9 plus x squared equals 8x. So radical 9 plus x squared equals 4/3 times x. Squaring both sides, 9 plus x squared equals 16 ninths x squared. 9 equals 7 ninths x squared. 81 over 7 equals x squared. So x equals 9 times root 7 over 7. Okay, so in the end, he should land this would be plus or minus because we are taking the square root, but negative is not going to help us. That would be in the other direction, and that will clearly leave him with farther to run. So he should land 9 root 7 over 7, or about 3.4, which would be much easier to measure if you're actually trying to row kilometers downstream.